This video talks about expectations of functions of random variables. And we're going to provide some examples with discrete random variables in this video as well. We know expectation maps a subset of the collection of random variables to some numbers. Those numbers can be expectations or expected values or average or mean or the first moment of the associated random variables. And we also know some functions of random variables are still random variables, so there are numbers, if well defined, to represent the expectations of those functions of random variables because they are still random variables, right? We can still look at the average of those new random variables. In this video, we look into expectations of functions of random variables and how they are linked with the original random variables. The first one is a very important result, which is the law of unconscious statistician, LOTUS. What is it? What is this one about? Well, we know distributions determine expectations, and the distribution of x determines the distribution of gx of this function of random variable. Combine those two conditions together, we know the distribution of x determines the distribution of gx and thus determine the expectation of gx. So the distribution of x determines the expectation of gx. And to calculate the expectation of this new random variable, this function of random variable x, we only need to know the distribution of x. That is the LOTUS, right? The distribution of x determines the expectation of gx. And to calculate the expectation of gx, we only need to use the distribution of x. So we don't have to derive the distribution of gx to calculate the expectation of gx. We can work directly with the distribution of x. This is enough for deriving the expectation of gx. Okay, let's take one example with discrete random variables. Suppose x is a discrete random variable with support x equal to a set of those elements. And now we look at this new random variable gx, a function of random variable x. What is the expected value of gx? Well, the expectation of gx can be expressed by this formula. It's again a weighted sum, but now we're gonna sum over all possible choices, all possible values taken by x, and we're gonna sum up all j small x with x from the support weighted by the probability of x equal to x. Alternatively, we can also work with the CDF function of x, right? Because for discrete random variables x, not only PMF function, but we know in general the CDF also determines the distribution. Right, here we have delta fx equal to this formula. Fx minus fy with y increasing to x. It might look peculiar at the first sight, but if we think about the graph of the CDF of a discrete random variable, right? Suppose this is the value x, and here what is the function of a? This is the a-axis, this is the y-axis. We know the graph of this CDF function would be look like right continuous, right? So at here, it's gonna jump by the value of probability of x equal to x. So if we look at the difference between fx and this limit from the left, it's essentially equal to the probability of x equal to small x. Well, if we order all the elements from the support of x in an increasing order, such that x1 smaller or equal to x2, smaller or equal to x3, then this function, this delta fx, can also be defined as delta, well, this expectation. Let's start with the expectation then. This expectation of gx can also be written as the summation of I gxi probability of x equal to small xi. Okay. So the I here again, we're gonna sum over all possible values taken by x, but now we work with the index of the small x's, which can also be written as the summation over all indexes small xi times the delta fx small xi. Now here, alternatively, we could write delta xi as the difference between fxi small xi minus f small x minus 1, right? By the definition, we know this is also equal to the probability of x equal to small xi, which is because fx small xi is the probability smaller or equal to xi minus the second one smaller or equal to x minus I minus 1 if everything is ordered in one increasing order. We know the difference here is essentially equal to the probability of x equal to xi, small xi. So both expressions works, and they give exactly the same results. Of course, here to make sure everything is well defined, we also need, in the second case, in the second expression, we also need to choose a x0 strictly smaller than x1, such that we know x0 is not from the support and fx0 is 0. Then when we work with index 1, it's also well defined, right? Here, if we choose I equal to 1, then delta fx x1 equals fx x1 minus fx x0. This one is equal to 0 by the choice of small x0. This is probability of x smaller or equal to small x1. But note, there is no other possible elements from the support of x that is smaller, strictly smaller than x1. So this is simply the probability of x equal to small x1. Then this second set of notations also works. They essentially express exactly the same thing, okay? So this is the example with discrete random variables, but there is one essential thing we have not discussed yet. Why this equation is true, right? Let's provide a proof. You can pause the video here and try to figure out yourself how to prove this formula. Okay, The proof with discrete random variables is kind of straightforward, even though the formulas look a little bit messy. All the steps are quite intuitive. The first identity here rules from the definition. So expectation of gx, we know x is a discrete random variable, then gx is also a discrete random variable. So by the definition, we know the expected value of gx is essentially a weighted sum of all possible values taken by this gx, weighted by the probability of gx equal to c, right? Then we sum all those terms together. Now let's take a look at this event. What is this event? Gx equal to c. Well, we can reorganize the event and write it as a union of event of x equal to a for all possible values of a such that ja equals the value c. Okay, so here, because we are choosing different values, different values a inside of this event, then essentially those are mutually exclusive events, right? This event, gx equal to c, is the union of x equal to a, such that a is from the support of x, at the same time ja equals c. There could be multiple a's, different a's satisfy this equation here. It could be a single. If there is only one, then it's just one. If there could be a1, a2, both satisfy the identity here, then we have a union of two events, x equal to a1, x equal to a2. Notice that those events, x equal to a, with different values of a, will be mutually exclusive events. Then the probability of jx equal to c can be expressed by the summation of the probability of x equal to a for all those a's, according to the axioms of probability. Right? Then we move from the first identity to the second equality. Next, we move C inside. And note here, if we work with those A, we know JA will be equal to C, right? So from this step, we replace C with the equal value JA here, because we know for all those A's, JA equals C, right? We didn't do anything. Simply replace C with the same number. Now let's take a look at the summation over here. So it sums over all possible values C, and then sums over all such A's from the support JA equals C. And given we are summing over all possible values of C, that essentially means those two summations together, we're gonna sum over all possible values of A from the support. Then we end up with the final expression here, which is the expression we have seen from the previous slide. So we are done. Okay, this basically tells us to calculate the expectation of Gx. The distribution of x is enough. And we don't have to derive the probability of Gx. We can simply work with the probability related directly with x. Let's take a look at one example. So suppose we have a random variable x that has outcomes 0, 1, 2, 3 with PMF function px small x. Okay. Now let's consider this new random variable x to the power 2. Apparently this will have outcomes 0, 1, 4, 9. You can pause the video here and think how to write out the expectation of x to the power 2 in using the PMF function of random variable x. The result is quite simple, right? The probability of seeing 9 from x squared is essentially the same as seeing 3 from x. Seeing 4 is essentially the probability as seeing 2 from x, and so on. In the end, it's easy to say that the expectation of x to the power 2, right, essentially can be expressed by this term. Only relies on the distribution of the original random variable x. Lotus. Now let's take a look at an alternative example. So here it's still quite simple because it's a one-to-one mapping, right? For different values of x2, there's only one possible value taken by x could achieve the such value. Well, let's consider alternative example here. Suppose we have a discrete random variable that has outcome -2, -1, 1, and 2. Now we still consider x to the power 2. Well, now the PMF function of x to the power 2 is slightly complicated now. So the probability of x2 equal to 1 is essentially the summation of the probability of of the original random variable equal to either 1 or 2, right? Either 1 or -1, and sum them together. And the probability of x to the power 2 equals 4 is essentially the summation of probability x equal 2 and the probability of x equals -2. Well, let's proceed to take a look at the expectation now. In this simple example, we can easily go with the definition of expectation, right? So here we can see that the first step is the definition of the expectation of discrete random variables, which is it only takes two different values, right? Either 1 or 4 times the associated probability. You can show that here we can express the k either equal 1 or equal to 4. That's essentially roots from the fact either the original random variable takes 1, -1, or 2 or -2, right? This also can be expressed in this way and easily checked by the formula above. So here we have 1 times the small x to the power 2 p1 with the PMF function of x to the power 2 plus 4 times now we plug in the fact they are also equal to this. So it will be equal to 1 times px1 plus px minus 1 plus 4 times px2 plus px minus 2. Look at the expression here. That is essentially the summation at this position. So indeed, we can directly calculate with the PMF function of the original random variable x instead of working with the PMI function of x squared. This is the second simple example. So hopefully from these two examples, you can see that Lotus is quite useful in practice, right? We don't have to derive. We can save this step, but instead we can directly deriving the expectation of x to the power 2 with the original random variable. And the second case we're going to discuss in this video is the variance. What is the variance? Well, the variance of a real value random variable x, if it exists, because it works with expectation, we know some expectation do not exist for some random variables, right? If it exists, this variance of x is essentially the expectation of a function of the original random variable. Okay, it's defined as the expectation of this new random variable, which is x minus a constant. The constant is equal to the expectation of the x and then to the power 2. The standard deviation is defined as the square root of the variance of x. Based on the definition, we can see directly the variance of x, as we have already mentioned, is essentially the expectation of a function of x, gx. So here we choose this function gx as the g small x as the x minus mu to the power 2. With mu is equal to the number is the expectation of x. Again, from Lotus, we know the distribution of x determines the variance of x, right? Because this variance is essentially a expectation of a function of x, gx. We know the distribution of x determines the distribution of gx, and the distribution of gx determines its expectation. Altogether, we know the distribution of x, according to Lotus, determines the variance of x directly. What is described by this variance, right? Why do we focus on this specific expectation of a function of x? Let's take one calculations first. Okay, so for any real valued random variable, this is defined as the expectation of x minus ex to the power 2, right? After some simple calculations, this variance of x is essentially the difference of the expectation of x to the power 2 minus the average to the power 2. Okay, the calculation is quite simple. Let's take a look one step by one step. So expectation of this random variable. Now let's first work directly with this random variable. X minus ex to the power 2 is essentially equal to x to the power 2 minus 2x times the expectation of x plus the expectation of x to the power 2. Right? Note here, on this side is a function of random variable. This side is also a function of random variable. Ex here is simply a number, right? And those two functions of random variables are exactly the same function, because gx x minus mu to the power 2 is essentially equal to x to the power 2 minus 2x times the constant mu plus mu squared, right? The same function. Now, by the linearity of the expectation, we know from the second step, we can move to the next step. And note here, the last one is simply a constant. And what is the average value of a constant? It will be the constant itself. Or you can regard the constant as a random variable, but only takes one value with probability 1. So the expectation of the constant is the constant itself, even according to the definition of the expectation of discrete random variable, right? We could regard the constant number as a discrete random variable, but only takes one possible values with probability 1. Okay, so the last term is just the number itself, and the first term, let's keep it, and the term in the middle, what is this value? Expectation of 2x times the expectation of x. We know expectation of x is simply a number. Expectations are numbers to random variables. So, and by linearity of the expectation, we know we can move the number outside the bracket, right? And again, here is a number 2. So let's move it outside. Then it's 2 times the expectation of x, a number, times the expectation of x, again, a number, right? Expectations are numbers to random variables. Then this is a number to the power 2. Okay? So this is minus 2 times expectation to the power 2 plus the expectation to the of x to the power 2. Then what's left is minus the expectation to the power 2, and the first one we just keep there, expectation of x to the power 2. But still, we don't know exactly what this one is measuring, right? It gives a different way of calculating the variance of x. To know the variance of x, we only need to know expectation of x to the power 2 and the original expectation. Then the difference between this expectation of x to the power 2 minus the expected value of x then to the power 2 will give us the variance, but it's still a little bit vague about what exactly this variance is trying to describe. So let's take a look one example here. Suppose we're gonna enter a mysterious door and we can get some payment xb. xb gonna be either you earn b euros or you lose b euros, and that is decided by a fair coin. So if you get head, you get b euros. If you get a tail, you lose b euros. The expected outcome always 0, right? So it's half probability you earn and half probability you lose. However, it's gonna be even though it's average outcome, average payment is always the same, but I bet it definitely feels different when we vary b from 5 to 0, right? So if b is always 0, then it doesn't feel anything. But if either lose 1 or earn 1, now start to feel something different, right? And if it's possible to lose 50,000 euros or earn 50,000 euros, that's gonna feel even different, right? So how do we describe those differences? Then we can rely on the variance. This is the graph of the values we have for for the variance if we choose different values of b, right? Because the variance of xb can be easily calculated, which is essentially equal to b to the power 2. Apparently from the graph, we can see that with larger and larger values, the variance is getting larger. And what happens with larger and larger values? So here we can see that the possible outcomes as b is getting larger and larger is spread far and further away from the average value 0, right? So the spread is getting larger and larger. So here, starting from the 0, then always 0, then we have b equal to 1, then either you earn 1 or lose 1, then it's 2. You either earn 2 or lose 2, and 3, either you lose 3 or earn 3, and 4. And we can see that the possible outcomes is getting further and further away from the expectation, from the average value, which is always 0 in this case. And the fluctuations around the 0, right, is getting further away from the average value, and the fluctuations around the average value is getting larger and larger. That is captured by the variance. So the variance essentially describes the spread of the random variables from its average. If it's spreading further and further away, we can see the variance is getting larger and larger. So if the expectation is described the average value, we can consider the variance is trying to describe the spread of the random variables. How far away those possible values gonna be from the average, right? Those are captured by those phenomena are captured by the variance. What are the properties of the variance? Let's take a look. The first one, for any scalars a and c from the real line, for any random variables, if the variance is well defined, then the variance of a plus cx is equal to the variance of cx. So we can shift a random variable by any constant value, and the variance will remain exactly the same. Right here we minus the value a, and the variance remains the same. If we want to move out a constant from the inside of the bracket, outside of the bracket, you have to, instead of using the original constant c, you have to use the c to the power 2, squared c. This one is easy to prove, because if we look at the definition of variance, what is the variance of this random variable a plus cx? You can pause the video at this moment and try to figure it out yourself. Okay, here let's continue. According to the definition of variance, we know it can be expressed in this way, right? To the power 2. Now, by the linearity of the expectation, we know we can move out the constant outside the bracket, right? So will be minus a minus c times expectation of x. Apparently here the constant term a cancels each other out. So indeed, when we calculate the variance of random variables, we can move the random variables by arbitrary constant. They're gonna cancel out anyway. So adding or minus or deducting any constant from a random variable, the variance remains exactly the same. Now we keep going, right? Now here inside, what's left here is cx minus c times a number. The number equals expectation of x to the power 2. Okay. Now let's take a look at this random variable. Okay, this random variable is essentially equal to this random variable, say to the power 2 times x minus the expectation to the power 2. Now this is a random variable. This is a random variable times multiplied by constant. And according to the linearity of the expectation, we know we can move this constant outside. And what's left here what is the expectation of this random variable? This is essentially the variance of x. So according to the definition, it's easy to check this one. If we shift a random variable by arbitrary numbers, the variance remains the same. If we want to move out a constant, you need to use the constant to the power 2. And conversely, if you want to move a constant inside the bracket, you need to take the square root. Okay? So this is the first property of the variance. A second property is also useful in practice. If we have independent random variables, x1 to xn, then if the variance exists, the variance of the summation is essentially equal to the summation of the variance of xi. Note here, we don't have any additional requirements for the xi's, but only require they need to be independent. Okay, this is the only requirements we have. Compare the properties we have for variance. They apparently are slightly different with the properties associated with the expectation of x directly. For expectation, we have for any random variables x1 to xn, right? The expectation of the summation is the summation of the expectation by linearity. And if we consider the linear transformation of x, expectation of a plus cx is equal to a plus c. Instead of c squared for the variance, it's just simply c times the expectation of x. Okay. Now let's consider a simple example to verify, to check those results. Suppose we have x1 and x2. They are IID Bernoulli distributed random variables, not only independent, but they also identically distribution. All right, have identical distribution and also an independent here, IID. You can consider this as flipping coins for 2 times, but a special coin, and only get head with probability value equal to p for each throw. Try to calculate the following values: expectation of x1, expectation 1 plus 2 x1, expectation of the summation, variance of x1, variance of this transformation, variance of 2 times x1, and variance of the summation. You can pause the video here and try to figure out those values yourself. Now, here are the results. So it's easy to say from those results, the expected values indeed satisfy the linearity requirements. However, for the variance, you need to be really careful, right? For this one, it's easy to say that the variance of 1 plus 2x1, we can delete the constant, does not affect the value. If we want to move out the 2 outside the bracket, that needs to be 4, right? 2 to the power 2 is 4. 4 times this value is indeed 4 times the variance of x1. And the variance of 2 times x1, right, is indeed what we have just discussed here. You can verify the results directly by the definition. What is the variance of the summation here? Because they are independent, the variance of the summation is the sum of each variance. And because they are identical, so each variance will be p times 1 minus p. There's 2 of them, so 2 times p minus times 1 minus p. Note here, if we compare those two values, we'll notice that the independence is really important, right? Without independence, we certainly don't have, for example, here, the variance of x1 plus x1 apparently is a summation of dependent random variables. And the result is certainly not equal to the summation of variance, right? However, if we have independent summations, then the variance of the summation is equal to the summation of each variances. Those values can be easily checked by definitions. Because if we have x1, we already have here x1 and x2, they are Bernoulli distribution and they are independent. We know x1 plus x2, they follows binomial distribution 2 and with successful rate p. And for this transformation, it's also easy to calculate the PMF. So all those values can be easily done by the definition. And we can use those values to verify the results we have just discussed over here. Okay, for this video, we have discussed 2 special cases of expectations of functions of random variables, and I hope you enjoy it. Thank you for watching this video.